So without further ado, I'd like to introduce David Aronchick, who leads the research and development at Protocol Labs, who are helping and organizing and deploying the community that's building the next generation of internet. David, the word is yours.
Sorry about that. Thank you so much for the introduction. I really appreciate it. Yeah, this was, I was first invited to this conference 2 years ago, just before the first pandemic, or the pandemic got going, and I was very excited to, travel to Budapest, and here we are 2 years later, still not in person, but I hope next year to be back and to do everything in person, so I can see you all. So today I'm here to talk about the SANE project, which is an effort that we have going on. It's been going on for about a year to simplify the way to approach cloud-native machine learning. And I'll talk a little bit about the history and show you a live demo of our most recent work. So one thing is that terms in AI and ML are weird. I'm going to make a lot of mistakes. I always do. When I say AI, that means artificial intelligence, and ML, machine learning. For the purposes of this deck, they're effectively equivalent. You're going to hear me also use the term experiment, run, pipeline, job. They're all basically the same. And for this deck, for this presentation, just think every time you hear me say the word program, that is the combination of everything, your algorithm plus your data structure plus your workflow all combined together. And an experiment is a single copy of it. So again, feel free to ask vocab at the end, but if I make any mistakes, I just want to get that out of the way. So diving right in, the thing that we run into the most when you get people in organizations and data scientists saying, I can't wait to go use ML, is how great it is. Every other day, there's some wonderful new study out there that is really transforming the world. And oftentimes, ML is the cause. One example that I was on the front lines for, that I saw happen in real time, was during my time at Google. Google cares enormously about data centers, data center efficiency, renewable energy, and so on. And one thing they wanted to do was make their data centers as efficient as possible, using the most amount of getting the most amount of compute for every unit of electricity. And the way they measure it is something called power usage effectiveness. So the goal is to get this as close to one as possible. 1 unit of power goes in, 1 unit of compute goes out. Unfortunately, today that's theoretically, real world impossible. You're always going to have some waste along the way. And owning and running a data center is oftentimes about managing that waste as best you can. So you want it to be as low as possible. And right now, this is where it is, high PUE, versus low PUE, and this is how they graph it. Now, they said, well, we think we have some really smart data center engineers. What if we hooked up machine learning to this and built a model to tweak all of our water cooling and fans and electric devices throughout the data center to make it more efficient? They did, they hooked it up and they ran it. And the moment they flipped on the switch, the thing just dropped, and they saw huge gains in efficiency. And just to prove it to themselves that this wasn't a fluke, the fact that they turned this on, there wasn't some other system. The moment they turned it back off, it popped back up. So you can see here, this is with the best data center engineers in the world talking about and improving their data centers, now using it. And once they used ML, it got this much better. So really dramatic. And this is what most folks see out there in the world. Unfortunately, the problem is that ML is quite hard. And it's not just hard because I'm bad at math. It's hard because there's this huge gap between where most folks are today, what their data looks like, how it's engineered, where it's sitting, and the magical AI goodness. And in between there's often a lot of pain. And the pain usually manifests something like this. You're able to develop a model very quickly that converges, that has great numbers, and you're looking, achieves your goals, but getting it out to production often takes a very long time. And in this case, it took 11 months and it still wasn't deployed. Now that was several years ago. I hope the model was deployed since then. But you do see this happen, very, very often. So users have two options today when it comes to bringing these models to production. The first is through something like a DIY, do-it-yourself approach, where you set it up from scratch, you integrate with all these existing legacy systems, and then you eventually migrate based on your business needs because platforms change and so on. That's okay. It does take a lot of work, and it requires a lot of humans to be committed to working on that ongoing. God forbid some key employee leaves. Oftentimes things aren't documented terribly well and so on. So a second path might be to use a proprietary solution. And the first 5 minutes of this proprietary solution is wonderful. It looks great. They give great demo, give great dashboard. Unfortunately, over the next 5 years, you oftentimes replicate all the challenges you had previously. You still have to set up from scratch. You still have to integrate with legacy, and you have to migrate based on your business needs. Plus, you're now locked in. So, if there was some brand new technology out there, it's very hard to move. Haven't we heard this story before? We have. This was the story that a lot of people were talking about, about 6 to 7 years ago around Kubernetes and containers, where people were building proprietary VM platforms, proprietary orchestration platforms. Docker, Kubernetes comes along, and it really revolutionized this open source, neutral way to roll jobs out and things like that. On top of the base platform, then we were able to now build cloud native apps. And that really was a transformative change. And it's something that really revolutionized the industry. So what would be great for us is to build something like cloud native ML. What would that look like? Well, in my mind, it comes down to really 3 key things: composability, portability, and scalability. Let me go into a little bit about what each one of these are. So for composability, what I mean is you were able to trivially build a model and roll it out. But oftentimes building a model is just one element of your overall platform. When you really think about doing ML, it's not just about the model. It is in fact about all these other services that go around it: data ingestion, transformation, splitting, training, model validation, and then finally rolling it out. And all of these components are often components that people swap in and out based on their technical need. This is a paper that came out of Microsoft several years ago talking about their own internal tool systems. And this is one of the most sophisticated data science organizations in the world. They have over 159 unique tools, each one of which may be needed for a different platform or a different component. So really composable needs. And so locking into a single solution that goes end to end will always end in pain for some large number of your people. Second is around portability. Today, when you think about experimentation, you think about having to specify all the things that go all the way down here to the base layer. From going beyond all those components that we saw on the previous page, which are just a portion of it. You have runtimes and drivers and OS and things like that. And you don't just have one setup of these; you have many, right? You'll have a second one for training. You'll have a third one for cloud. At each point, you're having to reset and reestablish exactly what the deployment platform is, which can be quite complicated and hard to do declaratively, certainly today. Things get very bespoke and specific. And then finally, scalability. So in this case, when people hear the word scalability, oftentimes they focus on things like infrastructure, which includes accelerators, cores, disk, network, whatever it might be. But it's more than that. It's also more programs. How do you run more programs through the system? You can see here, this is the number of NeurIPS submissions growing exponentially. And not just running a single program, but oftentimes running it many, many times over with slightly different permutations as you tweak your parameters. But then also more collaboration. You'll want to bring in your SWEs, your data scientists, bring them together, bring teams together, bring organizations together. At the end of the day, people just want more programs faster, but oftentimes there are many ways to achieve that. And you need to enable your platforms to scale very trivially. So that's what I see for the future for cloud native ML, which is great. And what's really good at that is containers and Kubernetes. Certainly that's a space that I know very well, but it really is built for all of these things to be swapped in and out with all these different variables and based on your specific business needs. However, if you want to use ML on Kubernetes, first you have to become an expert in all of these various components, containers, Kubernetes, packaging, so on and so forth, which is really not ideal and certainly not what data scientists are going to want to spend their time on. They're going to want to spend their time adding value, adding unique value. So the question is, how do we make this simpler and build something that gives everyone cloud native ML? So that's where we come to the SAME project, which stands for Self-Assembling Machine Learning Environments. The L is silent. With SAME, what you get is you develop a backend. In this case, it could be containers and Kubernetes or many other backends, and I'll show you what this looks like in a second. And then you define SAME, which is just that entire pipeline workflow defined at the notebook level, declaratively, and allow that to be rolled out into all of these various places. Big companies solve this by having their own internal platforms. Google has TensorFlow Extended, Facebook has FB Learner Flow, Uber has Michelangelo, Microsoft has Ether. There are lots of these platforms out there, and they're okay. But if you don't want to be a data scientist at a large organization, you're kind of out of luck. So let's solve it for everyone with a simplified SDK and toolkit that enables us to get there. But let's not make it easy. Let's up the level of difficulty and solve for where data scientists are today. Data scientists really don't want to go off and touch Jupyter touch Kubernetes at all or containers. The truth of the matter is most folks today are living inside their Jupyter notebooks. And that's great. Jupyter is a wonderful tool built by a great organization, really committed to launching and releasing new features as quickly as possible that really make data scientists' lives easier. And it's, to approach Jupyter, it's really many components put together. It's a file format, the IPyNB file, an IDE that people can interact with, execute specific cells. It's an execution kernel and a way for them to communicate back and forth. But then truly, it's a ecosystem of associated tools as well. And you really don't want to exclude that. If it's just you hosting a Jupyter notebook in the cloud, you're probably going to miss out on some of the best things that the Jupyter community provides, because oftentimes that's a proprietary hosted notebook that really is not available with the standard APIs and standard file formats that work for someone just going to their command line and typing Jupyter notebook. We also are seeing massive growth around Jupyter. According to several recent studies on GitHub, you saw 75% of quote unquote simple notebooks on Jupyter today. So these are really straightforward things that can be executed. They're just not. But you're seeing it just grow enormously. 2.1 million data scientists and ML engineers, according to a recent LinkedIn study as well. So when you think about the model development and deployment process today, it looks something like this. You start over here on the left, where you're using some tool to interact with Jupyter. Again, whether or not it's the file format, Jupyter kernel, or other things. Could be Jupyter, PyCharm, VS Code, Eclipse, you name it. The data scientist is going through her iterations. And then when she's done, she'll hand it off to a developer. Now, a developer oftentimes will do some form of conversion, maybe converting it to Python, maybe doing something more advanced like rewriting it in C or or Go or other, more cloud native languages than Python. Python's wonderful, but it is challenging to do things like multi-threading and so on and so forth. And so the developer is going to go and make that translation, try and do a lot of performance gains, and then she'll hand it to an SRE. The SRE will take a packaged element, could be a binary package, could be a container, could be any form of system, and then she'll build it into deployment artifacts and a runtime config, and eventually roll it out. So that might roll out to Kubernetes or Kubeflow, could be Azure Machine Learning, Vertex, SageMaker, you name it, Airflow, anything that understands how to execute that pipeline. But each one of those steps in between is oftentimes an opportunity for bugs, translation errors, so on, debugging issues and so on. And so when it gets down here to the lower right, that data scientist, who is the one who understands most about what the model was trying to achieve oftentimes has many layers to go through to understand exactly what's going on, which is really not ideal. The vision for SAME is to make it as easy as possible for a notebook developer to build that workflow inside the tool that she's already familiar with, deploy it locally, test it, make sure it works exactly right, and then enabled to be continuously deployed to production in an elegant way. And as a result, because all those steps in between are now streamlined, you're going to have a much clearer understanding of exactly what is executing in production and how to make it work properly. We are going to do this with 3 core pillars. 1, we want to make these notebooks portable. 2, we want to accelerate the path to production and solve that 11-month issue that I talked about earlier with an SDK that reduces boilerplate code and elsewhere. And 3rd, we also want to make this better and faster. Again, that original notebook has really no understanding that it might be executed in a complex distributed acyclic graph, a DAG, that could have caching, could have retries, could have reliability, all these various things. And we really want to enable that and enable it in a really trivial way. So instead of it looking like this, it now looks like this. She takes her notebook and is able to trivially build deployment artifacts, which are automatically deployed to her hosting platform of choice. This means if we achieve this, less inner loop, faster inner loop, less boilerplate. You limit the amount of manual rewrites you have to do, capturing deployment intent, and most importantly, you have this one tool chain for many platforms. Oftentimes, people might deploy locally to a local Kubeflow deployment, but then need to move to something like Azure Machine Learning, which is a hosted version that will enable deployment. And you don't want to have to retranslate that based on the backend. You also want to take advantage and use the best of the best 12 practices today, 12-factor apps, and so on. Okay, so that's a lot. What does this look like in practice? Well, let's actually show you. So here is a demo. This is live, as of last week's check-in. What I'm going to show you here is a roadsides demo. So this is a model built on machine learning to look at a data set and provide object detection within it to look at a series of images and tell whether or not you have a road sign. This is real live running code. All you can see here exactly what's going on. This notebook is a pretty straightforward notebook. It is serial, but it is doing lots of things. You have imports, you have system engagement. Here you have more imports, various functions that you're running through, a significant amount of time spent pre-processing the data, turning things into grayscale so that you can train faster, and splitting your data set here with all these pre-processing into valid, test, and train sets. Then running through the neural network built on Keras on top of TensorFlow, and then finally saving the model out finally. Now, as I mentioned, that is a model that works locally. We understand exactly what's going on, and it is able to converge, but it's slow. It's using my local system rather than production data and so on. And I want to move it into a more production-like environment. So for the same project, this is really trivial. All you have to do is add this API or this simple YAML here, which has some metadata, environment tags, which include a custom image that I've built for this, some names, and then some core parameters here. Again, pretty straightforward stuff. All I had to do was write this single YAML, and this is quite extensible. You can do it in a lot of different ways. Once I do this, now everything becomes code, and I can check all this in together into my GitHub repo and execute it automatically. But in this case, I'll do it from my command line. So let's go over to the command line inside my Jupyter notebook. And I'm going to go and type, you can see the notebook right there. I'm just going to type this command. Now I installed same before, but now we have a same command line, same program run, and I hit execute. And when I do that, it's going to go and push this to my Kubeflow deployment automatically. You can see it beginning to spin up here. It's going to just take a minute. because you have to download and begin running these. And it automatically injected several of these things into these steps in here. And you can see this is one that I ran a little bit earlier because it does take a little bit. But you can see as I ran this, it was able to, output all of these things, store it, run, pass between cells, so on and so forth. Very, very straightforward. And it ran much more quickly on this clustered machine than it did on my local machine. And then finally, at the end, it actually saved it all out to, my production model registry. But what you didn't see me have to do there was, as a data scientist, understand any of the subtleties of how Kubeflow works, or in this case, it also works on Azure Machine Learning. And we very much hope to support many, many other platforms as well. But you can also automatically, just with tags inside your Jupyter notebook, add additional steps, add additional caching, download from different data sets and so on, making it very, very easy. This is all live running code. I can't stress enough, this is very early, but it is out there. Everything you saw was real. You could actually go to your command line right now and type, pip install same project and begin to mess around with it, file bugs, join us on our Slack and see exactly what's going on. But at the end of the day, what we're really trying to do is simplify how easy it is to get out and move that local machine learning notebook into production. You can join us there on sameproject.ml. So with that, let me just finish this out here. What you saw a portable notebook. It was independent of the backend. It just worked. We support 2 backends today, and we would like to support many, many more. And so it's all about what we can do between now and then. Second, you saw an accelerated path to production, us taking care of automatically scraping for all the imports, importing it and building it in, all taken care of, and again, making your path as a data scientist easier. And you saw a very vanilla notebook with no special things executing on a pipeline. And we didn't show it here in the demo, but you can actually break this up into lots of different individual pipeline steps, again, without knowing anything about these complicated executions. A more complex same manifest might look like this, where you dictate images, mounts, resource, different services that you want installed, so on and so forth. But regardless, we're very much in the flight of building this. Regardless of exactly what we end up doing, the point of this is that the entire configuration and parameter and execution of this is now part of the declarative code that you can roll out, which is really a transformation. Instead of having hidden variables and parameters and things like that execute only on on a one-off basis and might often be lost, the execution is all now in code and recorded forever. We've gotten lots of great customer feedback, which is really exciting. We would love more if you can go and try it out, download it, let us know where we're broken. We would love to hear that. Or if you'd like to just jump in, we would love to hear that too. But at the end of the day, we really want a center of the Venn diagram where it's completely open source governed. This is a project without any company behind it. It is certainly, we are supporting it at Protocol Labs, but we would love lots more companies to come and help. We want it to be based on universal platforms that work anywhere. So whether or not that's Kubernetes or Jupyter or things like that, it should just work. You can adapt it to your proprietary, and we're going to have very clear ways to hook in and do that. But it is open source right now. I mean, it will always be open source, but we support all the open source platforms right now. And we want it to be declarative in deployment, where you know that I can go and fork this repo and instantly reproduce everything, and it'll just work. And at the end of the day, that is the same project. Like I said, what you can do, join our website, join our mailing list, join our Slack. We would love to have you in any of those specific things. We'd also love for you to come talk to us about your needs. We are looking for folks to co-develop this with. If you have a particular need, we would love for you to jump in. And most expectedly, or most powerfully would be to come join our repo. Try it out, build, complain about missing features, add your own if you'd like. Again, we are a very, very open project. And with that, I'm all done. Thank you very much. I really appreciate the opportunity, and I'm really excited. I would love for you to come help join and talk with us about your specific needs. And with that, yeah, let me know. I guess that's it.
Thanks a lot, David. Thanks a lot for sharing your knowledge and your expertise with us. For all our conference attendees, I'd like you to, if you have the time, to go to the polls and give David some feedback on what you thought. And David, we got a little Q&A session. You ready?
Hit me.
Okay. I'm going to start reading the questions. Tomasz Ileś, is SAME somewhat similar to Plumber?
I know of Plumber. Is that it?
Could be Plumber.
Okay. To be clear, there are many great workflow engines out there, particularly in the ML space. I know of Dagster, Plumber. I'm totally blanking on a great one. Oh my gosh, I can't. I feel so embarrassed. It's by Quantum Black, as released it. Regardless, what you're seeing here actually is completely compatible with that. So what happens is the notebook takes the image, or it takes SAME takes the image and injects a whole bunch of things around it. We can and would support many different backends. It's just a matter of how soon we get there. At the end of the day, those pipelines will abstract away the actual execution of those pipelines. And again, we don't want to be in the business of determining pipelines and how to run against them. So whether or not it's communicating with a layer like that or communicating with the backend, we're open to both. Over time, I very much think that we would love a framework interface to inject, and you just pick your framework of choice. But at the end of the day, something has to execute this DAG on the back end. And so far, that's the most popular one we've seen has been Kubeflow, followed by Airflow. But again, it's up to the community to help decide what we should focus on next. I hope that answered the question.
I hope so. The next question is from someone named Anonymous. What do I need to do to convert my notebook to your solution?
The good news is you have to do almost nothing today. That's the best part. We work on the IPyNB file, which is a standard set up by the Jupyter team, which we are really excited about. And after that, everything gets taken care of for you. So scraping it for imports, looking at using TensorFlow or PyTorch or things like that, encapsulating it in a container, converting that into a DAG that can then execute on one of these backends, and so on. All of that is taken care of for you. As long as you're using, so far we haven't run into too many bugs that require special one-offs or rewriting your code. But that really is a core goal of ours. The majority of notebooks out there today just work without having to do any significant translation.
Okay, very good. Thank you. Anonymous has a follow-up question for you. Do you support deep learning technologies like TensorFlow?
Yeah. So again, this is something we hear often. In many ways, that's what you're going to see the majority of the benefits around. If you're just, to be clear, if you're just running something like SciPy or NumPy or NumPy or Pandas, which are all wonderful frameworks for doing standard machine learning techniques, you're really actually going to see limited amount of value here. It's not that you're not going to see value, right? At the end of the day, being able to take your notebook, automatically converting it into a container and then running it on a production platform like Kubernetes is very powerful. And I don't want to dismiss that. But you could also achieve a lot of this with standard tools in the Jupyter Notebook community like NB-convert and others that would take that notebook and convert it into a Python file, and then you just execute that Python file inside a standard VM, which is fine and a great way to go about it. That said, the question was about deep learning, and that's where you really will start to see big value, because deep learning techniques often require embarrassingly parallel execution. That's where you take a single job and you split it across many nodes, which might have different resource constraints, and this step requires a GPU, and this one requires a CPU, or this one requires high memory, and this one requires fast disk, all those things. In many ways, this is very much a platform for these kind of like more sophisticated deployments. And as you saw there in the demo itself, we were all, the example is that TensorFlow example. So it goes and runs TensorFlow and using Keras, and it does that right there in line. And you didn't see any translation. That ran great locally and then ran great on Kubeflow.
Very good, very good. Next question is from Laszlo Sherman. Can we use SAME together with Apache Airflow?
Absolutely. You saw me put the logo there on the slide. That's probably the next platform that we want to support. The DAG for Airflow is very similar to the one for Kubeflow. It is truly just a number of human beings we have working on this, and we would love to support it. I myself wrote the Kubeflow adapter, and then I wrote an Azure Machine Learning adapter while I was still at Azure. The conversion from Kubeflow to Azure Machine Learning took less than a week, or building the backend for Azure Machine Learning took less than a week. I would guess that it would be similar for Airflow. It's just human beings working on it.
Okay, very good. Final question.
We don't support it yet. I just want to be clear. We don't support it yet. We would love to. And again, if you have specific needs or something like that, please come and tell us. But it is certainly on our roadmap.
Are you hiring?
Are we hiring? Yeah, I'm definitely hiring. At Protocol Labs, I am hiring like mad. I don't care who you are, what you want to do. Please come talk to me. You can email me. You can find me on Twitter. You can join the Slack channel. You name it. We're absolutely hiring.
Okay.
Outside of that, the project, though, to be clear, is completely open source. So even if you have a wonderful job today, but something like this would help solve your problems, we would love to help with that. So you tell me.
Okay, very good. Final question for you. Zoltan Gabor asks, you mentioned that developers do some performance optimizations on the Python notebook code before going to production. Is that included? Also, can you scale your computation as well?
So that's a great question. We're not doing any right now. We needed we optimized for compatibility more than for performance improvements today. That said, one of the core things we want to do as part of our SDK is build performance improvements in. So a trivial example today is running multi-threaded. If you are in Python today, the GIL, the global interpreter lock, requires everything to be single-threaded. There are frameworks and notebooks that help you run multi-threaded, and you can do it inside of Python, but let's just say it's not the easiest thing in the world. One thing we would love to do as part of our SDK is enable the data scientists to streamline what it looks like to do these performance improvements. So instead of just saying, execute this function, you say, same, this is a function, and I would like to run it multi-threaded. And then we will take that, translate that into multi-threaded code for you that you can run either locally or in the cloud. So the example is, I have a brand new, not brand new, it's a year and change old, but it's a wonderful Mac that has all these many, many cores on it and so on. But when I go and execute this locally, it runs on a single core, which is a super bummer because 9 other cores are sitting there what about me? It'd be great if we could automatically translate your single threaded app into a multi-threaded app on your behalf. And so that is a example of just getting performance improvements locally. Now, even better is what if we did that, but then also enabled when you went out and executed this in the cloud and did all these parallel executions, instead of doing it on a single machine with multi-threading, you actually spread it across many machines, right? Again, that'd be an enormous win. And a data scientist would never have to think about it. It would just work. So the broad strokes of what I'm saying is you can do these kind of performance improvements. We haven't done it yet, but again, this is absolutely part of our roadmap. It won't be hidden performance improvements. You'll have to do a small amount of I would like this function to be performance improved, in this way, cached or threaded or whatever, because we don't want there to be too much magic. If there is, oftentimes we're not going to capture the intent of what the person was writing. What was the second half of the question?
Couldn't quite, hold on. Got to put my glasses on for this one.
Sorry about that.
Also, can you scale your computation as well?
Yeah. So again, that would be the same thing. So one thing we will support as part of this is naming resource requirements per the steps that you dictate. So if you say, this step here is a low memory but high CPU, you can dictate what that execution will look like. If this later step is, oh, this is the step that requires a GPU, you could name that and say like, oh, this is a GPU step, I'm going to go out and execute on a GPU and then do that. And automatically that would be built for you.
Super. Great. I think I almost understand what you're talking about. But
Sorry,
anyway.
I know there are so, like, I every time I go and talk about this, it's amazing. The smartest people in the world are like, I've been out there building distributed systems my entire life, and I still can't quite wrap my head around ML. I'm 4 or 5 years into ML, and still every day I'm like, oh my God, what the hell is this thing again? So please, part of this job is to not have to have anyone understand it, just understand what they already know.
Great, super. David, thank you. Thank you so much for your presentation and sharing your knowledge and expertise with us. I'd like to show you a little something that we're going to be sending you in the mail.
Oh, that's amazing.
You know who that is?
I love it.
You know who that is?
That's me.
Yeah, it's you. And we'll be sending that to you in the mail as a token of our gratitude for you presenting at our conference today. So thank you very much, and enjoy the rest of your day.
Thank you so much. Thank you, everyone. Really, truly hope to see you all in person next year.